All right, here we go. New unit time. The unit is Unit 6, and it is all about these things called antiderivatives. Antiderivatives, right? It's going to be the opposite, the inverse of taking a derivative. And so it's basically going to be unwinding a lot of the processes that we learned how to do in the first semester. And so instead of saying, what is the derivative of this function? We're going to be saying, this is the derivative of what function? And so just like before, we're going to start today with just polynomials, and then we'll add on some of our other memorizer derivatives. So today the objective is to find antiderivatives, which are also known, slightly less commonly, but it's the exact same thing, as an indefinite integral. So the antiderivative of a function, also known as its indefinite integral, it's the inverse of differentiation, right? It's undoing that process of taking a derivative, right? To undo, to unwind, to undo, to flip, whatever you want to think about it. And it has a little bit of a funky notation. And so this is the notation right here. This is the antiderivative of f of x with respect to x. Sometimes if I'm being very sloppy that day, you'll hear me pronounce that dx, but it's really more proper to actually say it as with respect to, which you'll see me abbreviate as WRT, with respect to x. We'll get to that in a second. Those two things are always going to be found together. The integral symbol and the variable of integration, like slices of bread on a sandwich. They will always be together. You will never see one without the other. Okay. Now, the dx here, right, which I said is called the variable of integration, it tells us what variable we are taking the antiderivative of, right? So we did things earlier, like we said, okay, take the derivative with respect to x of x squared y, right? And remember, we said this was like using the product rule, 2xy plus x squared dy dx, right? And so it mattered what variable we were taking the derivative with respect to. If we took it with respect to y, right, you'd have a different answer. If you took the derivative with respect to y of this implicit, right, we did this whole unit on implicit differentiation. Well, now we'd have 2x dy dx y plus x squared, and the derivative of y with respect to y is 1, right? So it mattered what variable we were taking the derivative with respect to. For that same reason, you have to specify what variable you're taking the integral with respect to. And that's what the dx always tells us, or the dt, or whatever it may be. Another quick vocab word before we get to some actual, how does this work? The function that you are taking the indefinite integral of is known as the integrand. It is what you are taking the antiderivative of. And so putting that all together, this function here, the antiderivative of f of x with respect to x, basically means what function, if I did d over dx on it, if I took the first derivative of it, would give me f of x. There's one more key point here that really you have to see it to understand why. The answers to these problems, this is a very important point here, and it's going to make sense in about 2 minutes. You are always going to have a plus c tacked on to the end. That plus c is known as the constant of integration, and I will show you in a second why that is. Here we go. Find the antiderivative of 10x to the fourth. So if I were to translate that, I would be saying, basically, translate it into other math speak, the derivative with respect to x of what equals 10x to the fourth. Right, now this one's easy enough that you probably just think about it for a second. But here's how it worked, right? We're just doing the inverse of the power rule, right? And so we're unwinding it. And so here's how I like to think about it. Number one, the first thing, again, for polynomials, if it's sine, cosine, e to the x, it's all going to be different again, right? First thing I'm going to do is I'm going to increase this exponent by 1. I'm going to say, okay, well, I'm trying to do the opposite of the power rule. So instead of decreasing the exponent, I'm going to increase it. Because if I took the derivative of x to the fifth, If I took the derivative here of x to the fifth, I'd have 5x to the fourth. So I'm really close. I have my x to the fourth, but I don't want 5x to the fourth. I want 10x to the fourth. So you just think about, okay, what would the old coefficient need to have been? Well, it would have to be a 2, because the derivative of 2x to the fifth would give me 10x to the fourth. Now, I strongly prefer that you just kind of think about it this way, that you just think about it as, okay, like 5 times what equals 10, right? You just think about it that way. Technically, sometimes you'll see when this is taught, they'll just mechanically say, okay, now take your old exponent and divide it by your new coefficient. Yes, that's technically always the process, but I think it's a lot better for you mentally if you just think about, okay, 5 times what equals 10, right, 2. So we're going to have some like ones that get trickier with fractions, but the idea is the same. All right, now we're not done yet because, like I said, you have to add the constant of integration. So this is the final answer here. 2x to the fifth plus c. Now, why that plus c? And I'm going to use this to emphasize another super important key point. Check your answer. Check your answer. Check your answer. This is so straightforward to check your answer, but people will forget to do it, and it's very easy to make small mistakes here because you're like doing these things backwards. But you can check your answer. How do you check your answer? Go ahead, take the derivative of that thing. What is the derivative with respect to x of 2x to the fifth, right? Even if it's just in your head, right? Just check these things. Oh yeah, 10x to the fourth. Good, I got it. Here is why you need that plus c. What would the derivative be of 2x to the fifth plus 17? Also 10x to the fourth. What would the derivative be of 2x to the fifth minus pi? Also 10x to the fourth. Because of the fact that if you take the derivative of a constant, a number without a variable, it's 0, right? The slope of the line y equals 17 is 0. You don't know what plus or minus whatever number might be after that integral. So you always add a plus c to basically say, okay, well, it's 2x to the fifth, and then you could throw whatever number you want after it, and the derivative will still be 10x to the fourth. So you always throw that plus c on there. Okay, so let's see just a few of these in action, right? So a few just like rapid fire examples, right? Here's how I would think through this. Okay, x to the fifth, it's got to become x to the sixth, and then 6 times what would be 5? Well, 5 over 6, right? You're going to get a lot better at thinking through fractions as you do. That's probably the most important thing that happens this whole year. Not a joke. Okay, here we go. The derivative of, or the antiderivative of 4x, increase this exponent by 1. So this would be x squared, and then 2 times what would be 4 plus 2. All right, now this is a tricky one, but once you've just like seen it a bunch of times, you'll get it. 1 is really 1x to the 0 power, right? So this would be x. Or you can just kind of know, okay, what's the derivative of x? 1. We need our plus c, all right? And this is going to be our final answer. The last thing I would do is I would just do my mental check, right? I would do this derivative. Okay, the derivative of 5x to the 6th, 5/6x to the 6th, yep, that's 5x to the 5th. The derivative of 2x squared, yep, that's 4x. The derivative of x, yes, that's 1. Check, check, check. Right? Just always do that in your head. Couple more like random key points, right? Just if you have things that are not in polynomial form, you cannot just take, just like you can't just take the derivative of something like x plus 2 times 2x minus 3. You'd have to use the product rule, right? You have to get this into polynomial form. So the first thing I would do is I would multiply all of this out. So this would be 2x squared minus 3x plus 4x minus 6 dx, and then obviously that's 2x squared plus x minus 6 dx, and we could go ahead and we could take the antiderivative of this. Well, it's got to be x to the third, but we wind up with a 2x squared, so this is going to be 2/3 x to the third, and then we're going to have x squared, but this will be a 1/2 x squared, and then we're going to have minus 6x, right? Every time here, I'm just increasing the exponent by 1 and thinking, okay, what would I multiply those things by to get the coefficient of the original? Trust me, you'll get a lot faster at this. Plus c, and yes, I will forget the plus c at times, right? So always just be ready to shout at me on the Google Meets, be ready to shout at me, plus c, plus c, plus c. All right, two more. So let's see here. If we have this one here, same concept, just kind of emphasizing you cannot just take these antiderivatives unless they're in standard form. So we would turn this into, right, using exponent rules, subtract the 5, right? So x to the 7th divided by x to the 5th is x squared. Then we'd have a plus 2. Then we'd have a minus, and so this one's going to get us into our first negative exponents, minus 4x to the negative 2nd, and then minus 3x to the negative 4th. So this would be 1/3 x to the 3rd, right? You'll get so fast at these, you'll be doing them just like that in your head. Plus 2 would be plus 2x. Okay, now here's kind of one of the first sources of a mistake that's often made. Just like with the power rule for derivatives literally always says subtract 1 from the exponent, but people get confused when it's a negative sign. Same thing's going to happen to you here. The power rule for integration, you're going to add 1, but adding 1 to negative 2, don't fall into the trap. It's not negative 3, it's negative 1. So we're going to have x to the negative 1st, and I need to think about, okay, x to the negative 1st times what would be negative 4? This will be a plus 4, right? And so you can always, if you're not sure that part, just check yourself. What's the derivative of 4x to the negative 1st? Negative 4x to the negative 2nd. So you can always check those out here. Add 1 here, not x to the negative 5th, x to the negative 3rd, and that's already the exponent we want. So here we go, plus 1 x to the negative 3rd, all of that plus c. There's your final answer there. This also works for radicals, right? Last example here, this also works for radicals. You just have to, oh no, that comes from the next page. You also have to convert them, right? So this would be the antiderivative of 2 over x to the 1/2 dx, which would be the antiderivative of 2x to the negative 1/2 dx. So, okay, we increased the exponent by 1. This is x to the 1/2, and so then this must have been a 4x to the 1/2 plus c. Again, always, just check it in your head. All right, take the derivative. 1/2 times 4 is 2. 1/2 minus 1 is negative 1/2. Good to go.